Hey, let's review for the Module 2 quiz. I recommend you pause whenever needed until you got all these questions down. This is not necessarily all the material you need to know, but it is the bulk of it. We are reviewing the atom, the electron, the periodic table, and bonding. So, for the atom, provide the symbols for silver, mercury, and lead, and the names for CO, Na, and O. That's capital C, little o. Well, silver would be Ag. And I hope you're answering these on your own. Mercury would be Hg, lead is plumbus, Pb, and C with a little o must be the element cobalt. If it was a capital O, it would be carbon monoxide. Na is the German natrium, but we know it as sodium, and O is the element oxygen. What are the names and atomic ratios for hydrogen to oxygen for water and hydrogen peroxide? Well, atomic ratios are easy. For water, it's 2 hydrogens for every 1 oxygen. But for mass, it's different. Hydrogen, each atom checks in at 1 AMU, but oxygen at 16. I'll be using whole numbers. That means 2 to 16 or 1 to 8 for water. That would be the mass ratio. 2 to 1 is the atomic ratio. Hydrogen peroxide looks like 1 to 1 for the atomic ratio, but since oxygen checks in at 16 grams per mole, or AMUs, that would be 2 to 32, which is 1 to 16. Dalton's laws, the big one is that atoms combine in small whole numbers. But you should also know that atoms are considered to be tiny little indestructible particles. That's largely true on a chemical basis. Notice I'm not talking about a nuclear basis. Atoms of the same element are identical. That's true but you need to ignore a fairly large thing known as isotopes. And atoms combine in small whole numbers. They really do. I don't know of any ratio of greater than, say, 1 to 6 for atoms combining. All right, summarize Thompson's discovery. I suppose there would be exceptions to that if you're talking about sharing electrons. After all, atoms can combine to form molecules with thousands of atoms, or even millions if you include polymers, but I digress. Thomson's discovery, what was it? Yeah, it was the electron, and he did it with his cathode ray tube. He found something where the mass to charge ratio was so much smaller than hydrogen, he had to predict a subatomic particle. Rutherford, what was his discovery? Well, really, the other part. He shot a tiny little particle, which we now know as a helium nucleus, but back then they called it an alpha particle, at gold foil that may have been as thin as 1 atom, and it went right through, showing the atom is mostly empty space. The electron is in that void somewhere, but it's so tiny it makes no difference really, and the hard parts would bounce back or to the side would be the nucleus. In a word, he discovered the nucleus using the gold foil experiment. Summarize the Bohr model of the atom. That's one of my favorites. Although it only worked for hydrogen, he discovered that electrons reside in shells. And when they go up a shell, we call that absorption. And when they go down a shell, we call that emission. And what do they emit? Photons of light. If you want to investigate that further, look up the Balmer formula. It tells a really fantastic story. Okay, time for the electron. What's the electron? Okay, give it a try. I hope your answer said something like it is a subatomic particle. It is a tiny particle. I think it checks in at about 10 to the minus, I'm going to say 18 meters. 10 to the minus 28th grams. It's an elementary particle, meaning there's nothing inside it except the electron itself. And it is attracted to protons, which means it has a negative charge, and protons have a positive charge. Oh, and it exists outside the nucleus. Provide protons, neutrons, atomic number, and mass number for sodium plus 23, and then rewrite it. We call this hyphenated notation. That's a hyphen, not a negative sign. And we're talking about a single ion because it has a positive charge. It's not an atom. And it has 23 protons and neutrons total. That's called its mass number. And since it's sodium, by the way, I recommend you have a periodic table for this. Since it's sodium, if you check it out, you'll see that it has to have 11 protons. Otherwise, it's not sodium. Since it has a positive charge, it must be more plus. That means more protons than minus. That's electrons. So we subtract one electron. If we subtracted a proton, we turn it into neon. We subtract one electron to make it 10, giving us a total of, let's see, protons 11, neutrons must be 12 since 11 plus 12 is 23. Atomic number means number of protons. That is 11 all day long. And the mass number is right here, 23. And we are good to go. It didn't ask for electrons, but if it did, it would be 10. There it is. Oh, and here it is using the classical notation where you put the atomic number on the bottom and the mass number on the top, and typically the charge goes right there. So that's the way of rewriting it. Next question, summarize the relationship between wavelength, frequency, and energy with examples. Well, if you think, now we're talking about energy, which really isn't chemistry at all, but we need it to understand the electron because the electron is part energy. And as energy goes up, that's because the frequency of the waves is getting higher. They're almost like a machine gun, if you will. Much more frequent, much more energetic, much more dangerous. When the wavelength's long, like a radio wave, it's safer. Therefore, frequency and energy are proportional, but wavelength is inversely proportional to either one of those. As one goes up, the other goes down. An example would be a radio wave. It has a very long wavelength and therefore it's very safe, very low energy, very low frequency. Give the electron configurations for sodium and argon. Well, this is where you look at the periodic table and you follow the little leads, especially if you're using my periodic table that's included in this unit. You'll see that we need to account for 11 electrons in sodium. If you work your way across, you should get 1s2, 2s2, 2p6, 3s1. Have a look at the periodic table and have a look. If that made no sense to you, just go back and review that section, either in Blackboard or watch my little screencast. Argon is atomic number 18, so we have to go well into the third shell, and outbow order is always the same. So the first 11 are the same: 1s2, 2s2, 2p6, 2s2, 2p6. That brings us to, was that it? That might have been it. 1s2, 2s2, 2p6 is 10, 2s2 is 12, 2p6 is 18, and that's argon. You know what? I think this went out too far, did it not? 1s2, oh, right. Let's check it. 2, 4, 10, 11, that looks right. 2, 4, 10, 12, 18. This is correct. I might have said it wrong. But there it is. That is the 18 electrons. If you add up the superscripts, you should get the 18 electrons that argon has as an atom. What atom or ion has 10 protons, 11 neutrons, and 10 electrons? Let's have a look. What do you think? Well, 10 protons means it's neon. That's like its definition. 11 means it is neon 21 because it would be that isotope that has 11 neutrons, making it 21 as its mass number. 10 electrons mean it has no charge, so it is an atom of neon 21. How can you tell an ion for an atom? Well, it's actually very easy. Atoms have to have the same number of protons as electrons, like right here. If they don't, it's an ion. It might be an anion, which means negative, or a cation, which means positive. Time for the periodic table. Summarize the trends for increasing size, metallic character, ionization energy, mass, and electronegativity for the periodic table. I like to use diagonal lines since they typically point towards a corner. So if I take a diagonal line that's pointing down to the bottom left, that means something is increasing as it goes down or to the left. If I point it to the top right, it increases as you go up a group or across a period. And for the size, francium checks in at the largest. That's down in the left-hand corner. So that's down to the left. Metals are to the left of the staircase, but as you go down, they get even more metallic character. So we'll point down to the left for that. But really, I've never used that. I just say that anything to the left of the staircase is considered to be a metal. You'll see the staircase on the periodic table. Ionization energy is a nebulous term. It's the energy to remove an electron, although it doesn't necessarily say that. And it's very easy if it's, say, group 1, because they desperately want to remove that one extra valence electron in order to expose the noble gas shell underneath. So it's low to the left, high to the right. In fact, it's highest towards fluorine. Mass increases down to the bottom right since it reads like a book. If you see it as you go from left to right, things are getting heavier, and as you go down each shell, things are getting bigger. And finally, electronegativity, which is the desire for electrons, is super high for the halogens. They are the second to last column, and so it's highest for fluorine, therefore it is highest to the upper right hand corner. As an interesting aside, the noble gases sometimes are exceptions to these rules. Where is the dividing line between metals and nonmetals? On any good periodic table, you'll see a nice fat staircase. And a lot of the elements that are more or less on the staircase aren't quite metals. They're not quite nonmetals. They're called metalloids. They're semiconductors. What are the common names for the first, second to last, and last groups in the periodic tables? Those are the ones that have those old-fashioned names. First one, alkali metals. Second one, alkaline earth metals. Second to last, the halogens like fluorine, chlorine, bromine, and the noble gases, which are perfect, are the last column. Order these from lowest to highest energy. So let's think of lowest as safe and highest as scary. Infrared, visible, ultraviolet, radio, microwave, and gamma. Well, you might recognize gamma as being the scariest, so we'll put that last. Radio waves, although some people don't buy it, are quite safe since they're incredibly long wavelength and low energy. And I always remember visible as going from Roy G. Biv, red, orange, yellow, etc. And next to red is infrared, so it's to the left. That means on the safe side. And on Roy G. Biv ends in violet, and to the right of that is violet. So the safety progression would go infrared, visible, ultraviolet. So putting it all together, we would have radio, microwave, infrared, visible, ultraviolet, and gamma. Name these. These are just memorization, or if you have a table available, just look them up. You'll find that this is nitrite, nitrate, sulfate, hydroxide, acetate, cyanide, and ammonium. They are known as the polyatomic cations, and they're polyatomic ions. Most of them actually are anions, and there's a lot more. Time for bonding. Name me. CO2, Na2O, etc. I guess in case you only are listening to these, I'll say each one, then name it. CO2, that's carbon dioxide. Na2O, well, if it's a metal followed by a nonmetal, we call those salts or ionic compounds, and we do not use the mono-di-tri prefixes for them. So not disodium oxide, just sodium oxide. SF6, have a look, there is no metal present. Both elements are to the right of the staircase, so sulfur hexafluoride, we do use the monoditris. FeO, well, this is in the particular case. You'll look at iron is in the dead center. That's known as the transition metal region. You might also call it the Roman numeral region, because if you see an ionic compound in the dead center there, you've got to name its charge with Roman numerals, because there are many forms of iron oxide. This one must have a charge equal and opposite to the oxide, since ionic compounds are uncharged overall. Therefore, iron 2 oxide. NO3 minus showed up right here. That's a nitrate. NaCl is plain old table salt, sodium chloride. CO, you probably know just from everyday talk. It's carbon monoxide. Did you notice we use the mono? That's right, because it's not an ionic compound. It's a covalent compound. AlCl3, should we say aluminum chloride, aluminum trichloride, or aluminum 3 chloride? I would just say aluminum chloride, and here's why. Aluminum is a metal, chloride is a nonmetal, so this is an ionic compound or a salt, so we're not going to use monoditri. Should we use the Roman numerals? Only if it's in the center and it's not, so we don't. Aluminum chloride. FeO2 is a different form of iron oxide. Two of those O2s totals up to a -4 charge, therefore we're talking about iron 4 oxide there. Naming these things can be a pain. You might have to practice those. Okay, I'll give you the name, you give me the formula. Sodium fluoride. NaF. Check it out in the periodic table. You'll see that Na is +1, F is -1. Uncharged, check, perfect, one of each. Silver 1 oxide. Oh, they're giving us the charge of silver, so I'm going to write Ag. I'm going to remember it's +1. Oxides, I know if you check on the periodic table, oh, it's -2. Something's not right. I'll need 2 silvers to offset the oxide. Another shortcut is take that 2 from the oxide, put it on silver, take the 1 from the silver, put it on oxide. They call that drop and switch. And so it's Ag2O. Carbon tetrachloride should be pretty easy. Tetra means 4. CCl4. Ammonium, that's NH4. Oxide, that's O, but ammonium's +1 and oxide's -2. I'm going to need 2 of those ammoniums to offset the -2 on the oxide. So in parentheses, NH4, then a 2, then an O. Aluminum oxide, well, aluminum's +3, I think, if you look it up. Oxide, look it up on top of the periodic table, you'll see a -2. Ooh, in no way do those offset each other. We'll have to have 2 of the +3s to offset 3 of the -2s. Therefore, Al2O3. The drop and switch works great there. Sodium phosphate, sodium is +1. A phosphate, look it up, you'll see it's -3. We need 3 of the sodiums to offset the -3. Drop and switch is great again. Na3. PO4. No need for parentheses anywhere in that case. Only use parentheses when you have multiple polyatomic ions. Let me move myself here. And there they are, I think. And summarize covalent and ionic bonds. Well, covalent's all about sharing, and it's between 2 nonmetals. Ionic bonds are all about electron transfer, and they're between a metal and a nonmetal. The only exception would be the ammonium cation. There might be rarer ones as well. Okay, if that all made sense to you, you are in good shape to ace that Module 2 quiz.